Foi. Tá, eu vou compartilhar no Zoom.
Me lembra que eu tenho que buscar o microfone sem fio lá em cima, tá?
Tá. Foi.
Conseguiu? Tá cortando embaixo.
Tá, sim. Peraí.
Tá ótimo. Sim, tá ótimo.
Mas tá cortando embaixo.
Tá cortando embaixo. Acho que não tá no...
É que não tá no modo tela cheia. Onde será que está?
Não. Não.
Se eu tirar um
Qual é o
vídeo...
aplicativo?
Aí, foi. Não foi? Ah, não.
Não.
É que é um PDF isso, né?
Sim. Sim, mas tem full screen. Vai view. Full screen. Enter full screen. Isso.
Foi. Vê se você tá vendo no Zoom.
Sim. Pode ver, porque isso é muito bom. O que você faz aqui, ele vai... Bom, porque vai ampliar.
Tá. Beleza. Tá. Ô, Gilson, você consegue testar o pointer pra mim de novo?
Sim. Olha,
Perfeito.
aqui que você tem problema de...
Tá passando?
Eu vou tem que apontar para o computador.
Passou. Perfeito.
Pode ter.
Só
Pode
que tem
tirar
que
da
tirar
pessoa. Tira aqui. Tira somente ele primeiro. Deixa
Esse?
ele, sim. Ele. Não. Bora, porque agora ninguém está falando. Para ver ele.
Ah, então, é isso que eu quero.
Mas ele não está falando. Ah, então tira ele.
Só minimiza?
Sim, porque ele não vai aparecer, então.
Vê se tá aparecendo o Gilson aí. Tá, a gente tá aparecendo, tranquilo. Tá, então
Ok.
beleza. Gilson, a câmera tá aqui, mas... Só aquela. O mais importante é a apresentação. Tá escutando?
Você falou tem que ficar... não tem problema não, né?
Pode.
Ok. Alô?
Boa tarde. It's a pleasure to introduce Professor Vincent Girardi. Professor Vincent Girardi is a full professor of LHT. That is the National Laboratory of Scientific Computing, here located nearby me. And he is going to talk about cell segmentation, recent review, and challenge. Thank you very much.
Thank you very much for the introduction. Good afternoon. I'd like to thank the organization of this event. Thank you very much for inviting me. That's my talk, self-segmentation with the video challenges. Sorry. Something is not okay. Não está passando. Sorry, something is not working. Let's see if no. Não passa. Não passa aqui?
Do lado. Ué, o que aconteceu? E onde que a gente...
Está no full screen?
Não. Só
Né?
Aí, passou. Vai,
Assim,
tenta pelo
aqui.
pointer. Tenta pelo pointer, pera. Aí, foi.
Okay. So let's start. Self-segmentation with review and challenges. That's the agenda, introduction, so image acquisition techniques, image processing stages, challenges in cell image segmentation techniques, and final remarks in future directions. Introduction, stages of cell image segmentation. Everything starts with image acquisition. Then we can do feature extraction, image enhancement, cell detection, and segmentation. Segmentation is the main topic of the talk, and then classification. This is the basic pipeline. About image acquisition, The first possibility, optical microscopy. There are several possibilities in this subarea. Bright field microscopy, dark field microscopy, phase contrast microscopy, and so on. This picture gives an example that the same pattern visualized by different optical techniques. But here, dark fields, cross-polarizing, phase contrast, we see the same pattern visualized in different ways depending on the technique used. This cell example, bright field A in phase contrast, differential interference C, DAB are taken from the sense microscope. Now we see several too many objects to be segmented. Here, the problem of predefined or subject edges between rest and regions and the background. Here, too many regions to be segmented. And here, new image. These filaments are very important to be segmented, very difficult also to be segmented, structured. Now, electron microscopy, another possibility, could be made by transmission, scanning, or cryo-electron microscopy. Here, 3 samples. In A, we see several regions to be analyzed. The boundaries between the regions are more or less defined. In B, also many regions, but the boundaries are not so well defined. In C, cryo-electron microscopy, we see very noisy imaging. For atomic microscope, this technique visualizes several physical quantities. Each one gives a different visualization of the same structure. Here, we see, for example, map of height A in B, for solid adhesion, in C, viscoelastic adhesion, and in D, regular adhesion. Every visualization has its potential and also its challenge when considering image processing. Now, cell image stages, cell image processing stages. Yeast cells image, the original image. In B, we did the edge map extraction. Edge in this case is a pixel that belongs to regions with high contrast, regions that can be a border between the object and the nearby background. A post-processing is applied here, and we candidates to define the boundary of the objects are extracted. Edge detection is a kind of feature extraction, as we say. Image enhancement from A to B, we did an enhancement of the structures in order to better visualize the object of interest. In this case, this image was acquired by confocal microscopy. Cell detection and segmentation. In A, you have a cell detection example where each object is detected through a body box enclosing it. Neural network is a recent technique that can perform things like this. In B, a kind of segmentation, semantic segmentation. Every pixel is labeled according to background or region of interest. In C, segmentation. every pixel is labeled according to the instance of the object that it belongs. Here, classification. After segmentation, we can do classification as a traditional pipeline. Deep learning works different, but traditional pipeline for segmentation, then classification. Here we see bone marrow cell samples for class. The idea is an automatic algorithm that takes one of these images and outputs its class. It can be done by segmentation, feature extraction, and then a neural network or a machine learning approach to perform this test. Challenges in cell image segmentation, considering the image that we saw, number of target objects may be high, subjective and undefined boundaries, morphological diversity, irregular borders, lack of substate large image data sets annotated. Annotation in this area is a big problem because it demands hours, even days, of for an expert to annotate the data set in order to train a machine learning algorithm, for example, to perform the task automatically. So it is a problem in this area. And microscopic illumination effects. Application of cell image segmentation, just some examples, cell counting, medical diagnostics, patients have normal blood cells, counting sperm, etc. Tracking to follow a structure along a sequence of images taken along the time. And biology, cell size measurement, cell culture analysis, etc. Some background image segmentation. Traditionally, we can do segmentation by thresholding or through histogram analysis. This is a static example, just this value would be the intensity that separates pixels from the object, from pixels from the background. Sometimes it works, sometimes it does not work, depending on the application. This threshold can be obtained by histogram analysis or by some optimization techniques like entropy optimization, for instance. Multi-resolution approach from top to bottom, we did downsampling of the image. Sometimes it is easier to get the structure, to extract it, to segment the cell in the low resolution, and then go down to the original resolution to complete the result. Active control model, also called snake models, very much used until the beginning of this century. Here, just as that example, here the target object, the user places a balloon inside the object. This balloon will evolve through an evolution equation, artificial dynamics, composed by an internal force that controls the smoothness of the balloon during its evolution, an external force derived from the image contrast, and a normal force that, in this case, inflates the balloon towards the boundary of interest. The idea is that the dynamical system gets equilibrium nearby the boundary, and so when the balloon achieves the boundary, it stops the evolution and the segmentation is completed. That means pixels inside the object are belong to the target object, pixel outside does not belong. Has ongoing, like the watershed, even superpixels follow more or less this idea also. Some superpixel techniques follow this idea also. So we have a set of markers placed by the user or entirely automatic. So if it's labeled, we select an element of S following this optimization problem, and then so we get P star and L star, and then we label with L star every pixel in a neighborhood of K star that was not labeled yet, and put those pixels in S. We repeat steps 2 and 3 while S. The effect of this algorithm is to grow to complete this. Starting with artificial intelligence techniques, neural network specifically, which is a mathematical model of the human neuron. Here, the input of the receptor, to which edge it is associated away all the linear parameters called threshold. Weights are combined according to the linear expression, and F is an activation function with output 1 if the argument is positive and minus 1 otherwise. From the artificial intelligence viewpoint, the question is how to compute W and E such in order to solve a target problem. Classification, segmentation, etc. Here, a very simple algorithm. Sorry, was the font is zero, but basically we have the initialization, every weight is initialized with 0 in this case. Then we take an element of the training data set and then the desired result for that element. It is a supervised learning algorithm. This equation basically computes these expressions, and then we have the learning a mathematical equation that works as follows. If the desired result is equal to the output, nothing happens. If they are different, the weights are updated according to this expression. The steps 2, 3, and 4 are executed for the elements in the training data set, and we can show mathematically demonstrate that eventually we get the hyperplane. Perceptron is a linear classifier. Eventually we get the hyperplane that separates class A from class B. We can go a step further and arrange the perceptrons in layers to get a neural network architecture, a multi-layer perceptual neural network architecture. Here is just input nodes. Here the first layer of the computing nodes, called the IV layer, and then here the output layer. Every computing node works as a perceptron that works as I said before. And again, the problem is how to get the weights of the computing units, computing perceptrons, in order to solve a target test. The algorithm in this case is more complicated than that one that I showed. But basically, you have initialization and the learning rule. But basically, these are the basic elements. Results using traditional cell segmentation. Here, a combination between threshold and resolution. Here, pixels. The idea is to segment the structures, the regions of interest through by extracting their boundaries that the multi-resolution is a grid, a regular, rectangular grid with squares containing the boundaries in the low resolution and then project them to the resolution of the original. To be built automatically also. Here, an example of block cell acquired by atomic microscopy. Actually, one example for the contrast here is not good, but it is a global approach. We have two balloons. One balloon that expands from inside the object, and another one that contracts from outside the earth. When both balloons get closer, we stop that local evolution and use a dynamic problem approach to get the final results. Or another example is still in the context of traditional techniques, that means not using learning. That's what the traditional technique. That's the group of traditional techniques, so techniques that do not use learning. We have combination of superpixel and clustering, so the original data set is processed by a denoising technique. Then the superpixel approach uses superpixels are based on regions containing several pixels with some homogeneity in the intensity pattern. The superpixels of time they are processed by a clustering approach. The result is processed by a morphological operation to include the topology, the boundary, etc. And then we get the final result. Until 210, the situation was that solved. I forgot the reference, but here self-segmentation from using traditional techniques. That is the scenario here. We see an increasing interest in the community for self-segmentation. This quantity of papers in that time, and here the techniques used, threshold dominates, followed by finger extraction plus some machine learning approach, growing, performable model is here, and miscellaneous that composition of several techniques. After that, artificial intelligence takes place more intensely. Statistical learning, the neural network approach for self-segmentation. Support vector machines are traditionally a linear classifier also, but much more efficient than perceptron. It belongs to statistical learning area. Multi-layer perceptron with more than one hidden layer. When we have a network with more than one hidden layer, we saw a deep neural network. The deep learning area is composed by this kind of neural networks. Convolutional neural networks that compose the state-of-the-art in self-segmentation today, followed by attention networks and visual transformers networks that got the attention of the community in this area recently. Talk about convolutional neural networks. Here, a basic architecture. The principal operation here is kind of convolution. Convolution is defined by expression 7. U is the input image, H is the filter, a little matrix. And V is the output. W is a neighborhood around the pixel N, where we compute the result. Basically, this expression computes a linear combination of the pixels inside together weighted by the filter. Basically this. So we have historical the quality of the image, but the good image, it's not a cell just that it must be image like the ones that I showed you before. We have by image as inputs, we have image. Then we process this image using 105 filters, so we get a block with 100 by 100 spatial resolution, and that we go to the max pooling operation is used. Max pooling just reduces the spatial resolution of the initial block, but does not alter its path. Another convolutional lawyer is used in this case. 300 filters are used. Another max pooling that again reduces the spatial resolution of the job. It's a lawyer perception to the prediction. In this case, the classification. Regarding segmentation, the UNet architecture is very much used for image segmentation, particularly for self-segmentation. Here, in this schema, in this site, we have a combination of convolutions and max pooling operations. The original image resolution decreases while the number of filters increases. In this path, the right-hand side of the scheme, the opposite happens. The resolution of the image increases while the number of filters decreases until the last block that outputs the segmentation. The horizontal rows means chunking of information between these sides and the other side of the structure. This table is a sample of the complete table reported in this reference, which gives us an overview of the actual situation. 24 papers are reported in cell segmentation, and 23 papers reported for nucleus segmentation. The convolutional neural networks and UNet-like approaches dominate the scenario. Generative adversarial networks also appear, other kind of deep learning approach, followed by attention and visual transformers, but with less importance until now. This table is very useful because it reports also the data sets used to train the neural networks. So it gives an idea about the annotated data sets that we have today to train neural networks for cell segmentation. In general, the target is semantic segmentation. Sometimes the code is available, sometimes not. Here, tools for image segmentation, for image segmentation available, the same reference as before. 92 tools are reported. The links to the code and the links to the documentation. Here, the task. General self-segmentation, some of them perform also tracking. Tracking, in this case, would be done by long short-term memory neural networks, another kind of deep architecture used nowadays. In this case, also, in this case, also deep learning approach to dominate the scenario. Performance measures, precision we call, precision TP is true positive, and if false positive, and false negative. Precision is sensitive to false positive, while we call sensitive to false negative. Macro precision does measure average of the class precisions, and the same analogous for macro for. As we use for the macro precision, macro for this expression, and here intersection of union. GT is the ground truth, S is the segmentation, here the intersection, and here the union between them. When everything goes well, this quantity is 1. Otherwise, it's less than 1. Open problems in cell segmentation, high image size, too many image artifacts to be removed, presence of the object crowding, too many objects to be segmented, overlapping due to projection. Subjective edge and low contrast, insufficient, imbalanced, and inconsistent data rotations, which is a problem related to train artificial neural networks, deep neural networks to perform segmentation automatically, variability of the observed phenomena, specifically mainly for time-dependent phenomena. And when we have 3D data, these problems get one more degree of complexity. Final remarks in the research direction, handling big data and continually growing size. Every day we produce much more data that needs efficient algorithms to process and to extract information. Improving the quantity and completeness of annotated data sets, one possibility to mitigate these problems to use few-shot learning approach. That means techniques that use transfer learning or domain adaptation in order to avoid the necessity of too many data to train neural networks to perform segmentation. Prevention of multiple microscope techniques on the same sample, data fusion for self-segmentation in this case, is another direction. So, thank you very much for your attention. Thank you. Questions, please.
Any questions?
Does your model have the potential to be used for real-time microscopy video process?
Time is
Video process.
yes, it could be. But in the case of deep learning, this kind of data, or this kind of data, long short-term memory or visual transformers are more appropriated. Okay? Steps. That is more appropriated for static simulation.
Yeah. So, thank you for the talk. I've been working with a few projects related to image processing and further machine learning on top of it. And I was wondering which software you used to apply to your problems. Are you using, for example, TensorFlow or PyTorch or something fancier than that?
Okay, thank you very much. In my group, TensorFlow, basically TensorFlow, sometimes PyTorch. And they are but basically TensorFlow, we have used. Okay. Yes, even for segmentation. It depends on in fact, it depends on the experience of the students, no? It's, most of them use this test. Okay?
Thank you. Do you know of a better model or software, or you have a preferred model or software for big um, big tissue photos, like high open slice or neurosphere or something? Well, I'm not talking about confocal Z-stacking. If you have one photo of thicker tissue that has many layers, there's a better model or probably prefer.
So let's see, we have several slices of the same structure, and that's the point, several slices of the same structure.
Yeah, not necessarily to have many photos like a Z-stack of a confocal effect, just one photo of a thicker tissue layer.
So just one slice of, sorry,
An immunofluorescence picture of, let's say, 200 micrometer slice of.
but we have just one image, but
Yes.
the object has some okay. So in this case, let's see. Just one moment. Sorry, I'll get it. Please, turn off the light, please. In this case, probably you will have something like this, probably you will not see again, but overlapping between structures. And that's the point. The UNEP or the general CNN, fully CNN, will not solve the question of overlap. It's very difficult. Probably you will see, you should see a post-processing in order to try separate an object from the other when you have overlap. Unless the overlap happens different structures overlaps, so then you have different patterns, and then the neural network will separate them. But if the same object or some difference in the patterns from one object and the other. But in the training set, you should annotate this difference in order the network do this automatically. It is a difficult problem. Otherwise, no.
That's that.
Thank you.
Professor Francisco, pode vir aqui abrir o slide, por favor? Eu não sei onde vocês salvaram. Onde estão a próxima palestra?
Baixando o slide. Tá bom, gosto. Esse aqui.
Com dois, né?
Pronto.
Pode usar esse daqui.
Bom, bom.
Well, let's start the session, the whole session. The first talk will be given by Professor Francisco Alves, Professor at this University, our University of Rio de Janeiro. He is chairman of this conference. He will talk on modeling breast cancer progression from cellular data to clinical impact. Please, Francisco. Okay.
Hello? 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 Not work? What? Now is it work? Yes. Wait, thank you. So I'm going to talk about how to deal with things. Okay, I will talk about modeling versus progression from cell level data to clinical impact. Just take out the time. Okay. Okay. Breast cancer is frequently divided or classified for two types. Nominal A, nominal B, HER2 and the basal or tertiary negative. HER2 has bad prognosis, and the basal is even worse. And the frequency basal, right? Basal are related to metastasis.
Deve mudar o share screen.
Você acha?
Não fez o share screen. Volta no Zoom.
Faz.
Não sei onde ficou o Zoom. Cadê o mouse
Então,
aqui? Vai, então na reunião aqui. Aqui na flecha, aqui. Consegui.
Não consigo ver o mouse sumiu.
Aqui. Então, sai aqui.
Tá.
Sai. Aqui, ó. Não.
Mas o mouse sumiu.
Talvez porque está com esse.
Não. Pronto.
Não. Vai.
Aqui.
Sai, ele entra aqui. Não, esse aqui.
Aqui?
Sim. Esse aqui, vai aqui no share screen. Aqui. E vai na sua apresentação.
Qual?
Que essa aqui é a sua apresentação.
Não é essa não.
Posso, apresentação. Essa aqui, essa,
Não, é essa aqui.
essa.
Não.
Agora sim, agora está certa. E agora faz full screen aqui na apresentação.
Oh my gosh.
Ah, somente. Isso, somente na modalidade full screen da apresentação.
Já
Essa.
está lá, não?
Sim.
Tá.
Bom,
Obrigado.
fecha esse.
Não, já deu. É isso. Tá
Sim,
certo?
ok. Não aparece assim, não.
Tá bom, obrigado. Não, não parece.
Okay, yeah, first concept is
Se fazer full screen aqui, porque veja como está aqui.
Aqui, ó, deve ser a representaçãozinha.
Isso.
Não.
Não,
Já não tinha sido resolvido.
não está, não estamos no
Continuar, pode continuar.
okay.
full screen.
Não tem.
So that
Screen, back,
there are
screen,
some
screen. É porque
Isso aqui, que
ele tá em segunda tela ali, né?
O que tá compartilhando?
keys that
O share?
não, deixa assim.
Sim, mas é porque
Porque pelo menos tem que fazer assim. Mas
sim.
esse daqui não é full screen, entendeu? Aqui.
É porque ele
Esse
tá
aqui.
compartilhando essa tela ao invés de aquela tela, entendeu? Que ele tá, porque é pra lá, ele tá
É.
compartilhando pra lá.
Peraí.
O formato de compartilhamento
É aqui,
entra nisso.
foi.
Não, volta para lá. Volta para onde está. Volta onde está essa.
Onde é que tá a apresentação?
Apresentação. Vai onde está a
No
apresentação.
PowerPoint.
Não, isso não é.
Ponte, não.
Tem nada a ver.
Não.
Isso
Vai.
pode fechar. Esse pode fechar, não tem nada a ver.
Não tem. Vamos fechar aí.
Volta no Zoom. Porque, de fato, no Zoom, onde está o PowerPoint? Não fecha isso, né?
Eu quero ver que tá traduzindo. Como que eu chamo ele?
Volta no
Não, mas
Não é no Zoom, não é no Zoom. Não toca nisso.
não, nesse não, mas eu só vou tentar ver.
Não é no Zoom. Ele PowerPoint. Aqui, ó, PowerPoint.
E ele parou, gente. Ele parou a sala. Saiu ali, ó.
Onde é a sua apresentação?
Isso. Aqui.
Viu? Tá vendo? Ele abre o Zoom e volta.
Aqui, vai lá. Está aqui dentro.
To help solve this
Vai lá
this
dentro.
problem, I think that is what is more important to show to people here.
Ok.
If we cannot show in the internet, that's fine.
Ok.
Ok.
Okay, now it's fine. Thank you. Mas eu não consigo. Okay. So we have to ensure two points that the create the heterogeneity. Can have two cells transform into a negative one. The other question is so that CNF capability contributes to this transformation. So to answer these questions, we had some data that was in fact already published on this paper. But now we are using this data to calibrate our knowledge. So what we have in this data, we measure the level of the AF kappa B and some genes that are targets of AF kappa B and are involved in the metastasis. So they found that the level of AF kappa B in a healthy cell is much lower than in a negative cell. The same thing for sludge, twist, and C1. Okay? So these are the data we are going to use to calibrate our model. What the model, the model is here. The model is just a representation of the model. On this model, we are describing NF kappa B self-activation. We are using some experimental result from the literature. So these results show that NF kappa B activates the subunit P50, and also the unit is 65. With both units together, they bind together to form a capability diagram. And also in this model, a capability activates the blood C1 increase genes. This model, we are describing the gene regulates as a two-step reaction. The first reaction is the binding of the transcriptional regulator. After that, we have the sequence of the gene RNA, and the following step, we have the sequence of the protein. So I'm not going to show the details here, but I can show you here the set of differential equations. Then we use the software Copasi to calibrate these differential equations to our data. And here we see the result of the calibration. See that we have good calibration. So the next step now is to use the model to help us to understand the data of the system. So we found that the model has two stationary states. This is a bistable model. We found that the model has two stationary states separated by one unstable one. Okay? And our calibration was able to associate these stationary states to the level of expression of HER2 type, and the other stationary states was related to the certain negative stationary atoms. So what we can see here is that the kinetic parameters, they are the same. In the same kinetic parameters are generating these stationary states and these stationary states. Okay? Making linear instability analysis, we found that the stable stationary states have seven negative RD values. Okay, that's stable. But what is more interesting here, but it is not surprise, what is interesting here is that these unstable stationary states has just one positive ID value. It seems that this is unstable, but not so much. This is unstable just because one ID value is higher than this. That's very important. So, then we use the quasi exponential relation to determine the gene regulatory network landscape with the attractor basis. So here is the epigenetic landscape, the model epigenetic landscape, and we can see that we have two bases of attraction. One base is associated to the HER2, and the other one negative. Here is another view of the same surface, and here is just down view. So we can see here that as we see here, this is the stable stationary space, that one is stable too, and this one is not stable. Okay, we use a lot of stochastic simulation to generate this surface. So now this is the analysis of the model considering the deterministic behavior. So the question is, what about the stochastic behavior of the model? To answer this question, we can show here stochastic simulation with one cell that is starting from the strictly negative surface. So we can see, as was expected in the stochastic simulation, the concentration fluctuating in the strictly in the HER2 subtype. Just need to wait a little bit, and see that at some point the system will move from the HER2 base of attraction to the strictly negative base of attraction. So now we have another representation of the same system, and here this is a 3D representation, and I show you here some eigenvalues, some eigenvectors of the differential equation. We can see that the model is fluctuating along this stationary state that is stable. This one is the unstable eigenvector. That's the eigenvector that has eigenvalue higher than 0. And we can see that the system is fluctuating along this eigenvector, but we can see that it visits the one that at some point move to the other one. What is interesting here, and I must tell you that it was surprise to me, is the following. Is the following. We can see that this unstable stationary state is mediating the transformation of one stationary state to the other. So the first result we have is that the stochastic fluctuation induces the hair to a very negative vertical transition. So what I showed you was the result of one simulation. What if we run 120 simulations? If we do that, we will see that we are going to have the transition at different times. It's stochastically distributed. So here we can see that after 20 years, we start from 0 cell at the triple negative state. See that the number of cells, the triple negative states is going up, and the number of cells they are to reduce. Of course, the cells in the heart to type is moving, is transitioning to the triple negative subtype. So we can see here that with this simulation, we can reproduce these experimental results. We see that after 1.6 years, we have this type of heterogeneity, where around 60% of the cells have already moved from the HER2 base to the negative one. And after 7.5 years, we had almost 45% of the cells had already moved from the HER2 subtype to the triple negative. So we are then proposing an explanation for these results. And we can say that the stochasticity at the molecular level gives rise to cellular and tissue level heterogeneity. What I say here is that the stochasticity in the level of expression of NF is induced the transition from HER2 to negative. However, this transition is stochastic. So we have the stochasticity here in two levels. The molecular level, and this molecular level of stochasticity generates the stochasticity at the cellular level. So, now adopted results. And finally, here it shows another representation of the simulation we already see, we already saw. And I don't know if you remember that for 2 times the system moved from this IP vector to this one. Just to make you remember that this IP vector is the IP vector associated to this stationary state. And this IP vector is stable. It has IP value lower than 0. But even though the system was able to stay from this stable IP vector, the system was able to escape to this stable IP vector and jump to this one. Remember that this state here is unstable. So this eigenvector is the one eigenvector that is unstable. So this is but to explain why when the system jump to this eigenvector, it moves back. It jumped two times. It jumped at that point, here side, and here it's jump again, but in the third time, when it jumped to this unstable one, it was able to reach the other side of the daisy. Then, after that, now it moved to the other side. So, what we can say now is that we can say now that the weak eigenvector drive the transition between neighborhood bases. What is happening with the eigenvalue of this eigenvector is very interesting. This eigenvector, this eigenvalue is higher than zero. If this is higher than zero, it indicates that this stationary state is unstable. However, this eigenvalue is lower than 1. It indicates that this is weak. So that's exactly each state explain why the system is using this unstable state to move from one stationary state to the other. And what is more interesting here is that the system will never come back. It's exactly what we see experimentally. Unfortunately, one cell that moved from HER2 to territory negative, it will never come back. This is exactly what we see here. How long time do I have? So then, now, so it looks interesting. The question is, how, what is the impact of this in the bench or in the clinics? So we found the very interesting experimental results that show that these protein that is involved in the degradation of P65, if we make mutation on this protein, and if we increase the degradation of P65, we decrease cell proliferation. If we decrease the degradation of P65, it increases cell proliferation. It makes sense. It is those areas that if we reduce the amount of P65, we reduce cell proliferation. So the question is, can our model explain that? We simulate this behavior in the model, and the model shows that if we reduce the amount of P65, the base of attraction for HER2 now is larger. Because it is larger, the probability of transition is lower. So it explains why reducing the level of P65, we reduce the urban fertility. So I will finish here because because of the time, and I want to show here some people who are available. Thank you.
So, there are either comments or questions. Please.
So you say that we have B65 regulation, but since the system controls both the B50 and B65, why do we on one? And we require this make line? How is that going to be?
Yeah, what's happening is that if we reduce the amount of the 65, we are going to have less diagrams. So with less diagram, we have less self-actualization.
Does that also result in less B50?
What?
It also results in less B50 as a consequence.
Less, yes, exactly. Yes, because if we reduce the amount of linear capacity diagrams, we must remember that the background base of the same, so we reduce the thickness of the but we not change the degradation, so the amount of difference will also.
There are other comments or questions? Please.
Yeah, Francisco,
Yeah.
I like very much the fixed point analysis and stochastic region. I have one question though. Your analysis is in minutes, in days, but for what I saw, you didn't make any inference of the parameters. So how can you tell if there is minutes, days, or if it's a random units your time?
Yeah.
Thank you very much.
Yeah, in fact, we have the simulation are 20 years. We took 150 simulations for 20 years in the water time. They after 20 years, all the cells shift from one stationary state to the other. If it's not issued in your question, I think that is not understanding.
Is that how did you parameters in your model? Like you use it data to like make inference of the parameters of the genetic parameters of your models.
I'm sorry. I'm not.
You did a fixed point analysis. So you use it a random parameter like K1, K2, K3, you didn't fix any of them or like 0.1 molar per time. So how can you make a simulation that goes around 20 years if you don't have any units in your parameters, if you don't have any parameters at all? So how can you do a simulation?
We don't have the parameters of the model. We have the financial parameters of the model. It's here what we are doing and the that and this differential equation. Then we add stochastic white noise. Then it makes the concentration fluctuates. I had this parameters as I just did not have that, but I can send you the link for the print, and I hope soon they later.
Every time I hear this, three plants, interesting, so I was wondering, one key feature of this dimerization. That was talked about earlier, the positive feedback of my brain. Whether that dimerization, what extent that dimerization was really important for the work. Makes that simply by an FME entity that has positive feedback. Why not? Or match it then with effects or synergies by a
It seems to me that you are asking me about what is the effect of diagonalization.
Yeah.
The answer for this question will come from our postdoc. She is going to make a differential system analysis using very tools, and they should identify the effects of each of the kinetic parameters. They need to be able to check how important the dynamics. I think that it will be very important, but we must wait my other results.
But could also, I think that's going to be great, but you could also simply replace your current model topology with just an NF-kappa-B that provides negative feedback. Right? And so, anyway, if that's done, you could also think about either that P75 that also polarize that provides positive feedback to the cell. It's a minor component. Dimerization is low affinity. It's not the preferred. And I believe that it's possible. So there are some variations to this that might actually make if it's an important component of the model, very interesting.
Yeah, this very recently for sure I will check that if I will give you soon the more precise answer. But what I think you will now is that since this self-regulatory model, it will be bifacial. For sure, we are not going to lose by instability with this kind of change at all. But maybe the attractor base will be selected. And maybe we are not going to have this unreversible character. Because what is hidden here is what makes this model different from the other models. That majority of the model are symmetrical. We have this transition, but we can have this transition effect. And I feel that what makes the system to be asymmetrical is exactly the possibility of diversity.
But you have two attractors, but the eigenvalues, negative eigenvalues of the two attractors keep they're not the same. No? The relative eigenvalues of each attractor, they are different.
Yeah.
So one of them is less negative than the other.
So yes.
So it's more difficult to escape for the attractor when the eigenvalue is more negative. Because and you can go from one to other depending on the intensity of the noise. If you put the noise high enough, you can change.
But we must check that the only effect is not the intensity of the noise, but the size of the base. See here that this distance here from this state to this one is lower than from this state to this one. So it will be very hard for the city from here to reach this point. This is another novelty of here. The shape of the basis is very strong.
And all the topography you have here change if you change the parameters of your equation.
Exactly. But I don't know how much gains, but I assume I know.
So let's start the Francisco.
Thank you.
And- Professor Noel Garden. Name, French name. But he is professor at the NCC, National Laboratory of Scientific Computation, in Petrópolis.
Eu tô.
You talk about nuclear prospecting, integrating artificial and computational intelligence with the Nordic or the DS platform. So let's wait a little bit.
Pode fechar o seu.
É isso.
Porque não foi transmitido, entendeu? Por
Não
isso
foi?
a gente estava. Não, é por isso
Ah.
a gente estava
Sim,
aqui.
sim. Pois é, mas
Ou seja, você apareceu, mas numa apresentação.
Acabou resolver aquele problema.
eu tô tentando agora achar a do Lohan.
Não, mas é somente.
Não sei.
Volta somente um Onde está a apresentação dele? Deve identificar a
Pois é,
apresentação.
deveria estar, mas não tá.
Então, faz share, porque aqui senão ele vai ficar em nulo, entendeu? Você faz assim.
Não, então. Você quer fazer? Porque eu não estou sabendo.
Espera, esse aqui é um stop share. Primeiramente deve sair.
Mas a apresentação dele deveria estar aqui. Eu já abri. Eu já abri, só que
Você
não fechou.
Sim, desculpa, a sua reconheceu. Não, espera.
Não, é que sumiu. Por alguma razão sumiu a dele.
Então, deve abrir primeiro.
Eu já fiz o download, já deixei aberto, mas sumiu. Eu vou fazer de
Primeiramente
novo.
abrir para reconhecer, entendeu?
Eu sei, mas eu tenho que achar,
Ah, sim.
Gardenia aqui. Eu vou ter que baixar de novo.
Tá bom, mas calma. Melhor
Gardenia.
5 minutos.
Qual é a sua aqui, Gardenia?
Vai lá.
Pronto, aqui.
Isso.
Essa é a...
Esse dele, não?
Eu vou.
Agora, momento.
Ah, você quer falar aqui?
Não, quer falar.
Nada.
Momento somente. Espera um segundo, é um momento que somente eu vou abrir o
Você
Zoom.
consegue?
Vou ver, espera. Aqui, ó. Como eu fiz isso? Não. Espera, que eu não consigo. Não, espera. Eu não consigo abrir o. Aqui está, sim. Ok. Screen. Não sei por que aqui abre. Espera. Tem muita coisa aberta aqui, por isso. Será que então aqui. Cadê onde foi? A apresentação.
Esse problema?
Sim, porque não aparece a barra aqui. Não tem barra aqui, entendeu? Não aparece. Desculpa. Aqui usar isso. Mas não tem a barra, é muito esquisito isso aqui, entendeu? Assim, olha. Eu usei um Apple. Não, mas não é isso. É um Apple esquisito, porque assim.
Mas é.
Cadê o
O que é?
Zoom?
Tá PDF ou é que novo?
Não tem.
Só pelas perguntas, então.
Não aparece os ferramentas aqui embaixo. Não. Cadê?
Tá do lado.
Onde é do lado? Cadê do lado? Por isso a gente não consegue entender, porque não aparece onde estão.
Aqui.
Então, abre do lado
É
do
o
Zoom.
quê? É PDF ou é o quê?
Aqui.
Esse abre o Zoom também.
Ali, ó.
Sim, mas espera. É isso. Senão a gente não consegue abrir. Então, a mexer.
Não, você tem que fechar e tentar de novo.
Não, mas
Mas não vai aparecer o do Lohan aqui.
Não, mas esse aqui, não? Esse? O seu?
Esse.
Conhece? Esse?
Esse? sei. Não.
Esse aqui.
Deixa eu fazer aqui. Deixa eu tentar. Coloca esse aqui, que não vai dar. Agora a gente. Agora sim vai aparecer o dedo. Qual é o seu aqui? É esse aqui, né?
Esse.
Agora sim. Agora
Tem que botar a tela cheia, já tá a tela cheia.
Sim, já, deixa assim, é melhor. Não vamos complicar.
I'll pass the slides. What's possible to pass the slides? No? It's here, yes. It's here, yeah, it's okay. Maybe because it's not in presentation. Presentation, no? Full screen. Try to see. Não está funcionando essa parte.
Espera.
Vamos sair de novo.
Não, porque talvez tenha muita coisa. Tem muita coisa conectada, entende?
I have to change lá? No.
Mas isso daqui está conectado. Ó. Sim.
Screen sharing.
Não, isso aqui, isso está no Zoom. Então, se tirar aquele no...
It's here, né?
Não, isso vai sair. Não toque aquilo que...
It's preview?
Não, esse é preview? Acho que é preview.
É PDF, sim? É PDF. Então é o preview, deve ser.
Esqueci de mostrar.
Tem que chamar o Francisco, né? Francisco.
Falei, melhor não deixar full screen, deixa.
Mas não estava mudando a página. Não estava mudando a página. Aí quando você bota, às vezes muda, mas não mudou também. A página não está mudando.
Não tá? Não. Mas tá no full screen, tá tudo certo, mas como é que nós estamos mudando?
Tá cheio.
Agora tá, né?
O que fez? O que você fez?
Depois te ensino.
Tá.
É só
Tá, não?
clicar aqui. Você clicou, não, né?
Não está funcionando aqui no... tá.
Agora tá se você clicar, você ativa.
Especially for the carrying stations, especially Francisco. And in my presentation, I will try to show you the development of the Docker project in my research group at XC, and also the development of new methodologies using artificial and computational intelligence. Developing the drug is a very expensive, time-consuming, highly efficient process. And the idea is to develop with computational methodologies to speed up and reduce the cost of this process. In structure-based drug design, the idea is to develop new methods that use the three-dimensional structure of a molecular target and the three-dimensional structure of a small ligand to try to find the conformation, the native binding poles inside the cell of my site. With this geometric formation, it's possible to investigate the main types of molecular interactions and try to modify the ligand in order to obtain a ligand more potent and with more specificity against our target. In circular drug design, one of the main methodologies used is the molecular hopping. We have to face two big challenges in molecular hierarchy. One is to try to find and correct that may fold inside, right inside the molecular target. And the other challenge is to try to predict correctly the binding affinity energy between the receptor and the ligand. And in a visual screening experiment, we try to identify the most active molecules in a library containing thousands, millions, and even billions of compounds. And if you use computational intelligence, for example, mais parte da algoritmo genético, algoritmo for the binding prediction, and you use machine learning, for example, for all the aspects of this process, binding mode prediction, discriminate between actives and inactives ligands, and to predict correctly in the binding affinity free energy in the receptor ligand, not to order correctly over the ligands of a library. We have been developing the doctor program in the last 20 years, I think 16. The doctor program was released in 2013. The doctor website was released also in 2013 for only 1 million against one molecular target. And in 2018, we released the version of the website for visual screening. It's a free, we have 100 users up to 200 compounds. And for registered users, you can submit jobs up to 5,000. And the version of the website is predicted to be released in the next semester or the first semester of 2025. And today, the doctor project, the doctor website, the facility for free facilities provided by the supercomputer Dumont. A user can access the web server, prepare a job inside the web server, develop an experiment, submit this job to be run in the supercomputer. When the job is finished, he receives an email and is redirected to another page of the web server to analyze the results. And all this is free, all this is open, and all this is running science. The doctor program is a grid-based the doctor program where the energetics of the protein is made in a grid covering the active site of the protein. The protein is considered rigid, but the sampling of the ligand configurations are made inside this grid. And the doctor program was developed to deal with highly flexible ligands. We developed our own multi-solution algorithm. We use the MMF 94S spatial force field for close prediction. We develop our own empirical functions for magnetic predictions. And a very important point, the parameterization of the receptor, the ligand, and constant is totally automatic. That will mean that the user to be a molecular modeling expert. All the code is included and is discussed. And a very important point of the doctor program that the multi-solution algorithm in a single run, we try to obtain a set of important binding modes. If we have success, we can predict the negative binding modes and alternative binding modes for a single ligand. Another point, a very important point, that we use a classical force field with more than 20 parameterizations from 20 functional groups, and both the ligand and the protein use the same force field. And very important, we don't need to perform quantum calculations to calculate the atomic partial charge. These partial charge are calculated taking into account transfer parameters, sharp transfer parameters, looking for the covalent environment of the atom. To validate our docking program, we have to perform a dock experiments where you take some receptor leading structures, experimentally determined, and try to predict the deposit side using the original structure of the target. You compare this predicted in the experimental pose. And if you have a routine square deviation less than 2 angstrom, your dock experiment is considered excellent. Here we have a comparison. We compare the dock program with other programs like very programs that are well used by the community that performs dock experiments like Gold, Glide, Autodoc Vida, and we notice that the results. The results are comparable all the state-of-the-art programs in the dock experiments. We also evaluate the program in a very in training sets with more almost 3,000 complex, and we observe that looking for the best energy pose, we have success rate between 66% and 75%. The difference is because this small sets create many cases create automatically. But that's something very interesting. If you observe the other alternative bite nodes, if some of them are similar to the native bite node, we obtain success rates close to 90%. And now we are trying to develop exploring strategies to increase to identify the alternative other bite nodes in order to classify correctly as native nodes. Here we have some results showing that Dr. Is very good for dealing with highly flexible ligands. This is a very hydrophobic ligand, and Dr. has a very good result, 2.07 angstroms. Here is a very polar system with more than 20 rotational periods. But the root sphere is very low, 0.73 angstroms. And here's a special one, it's not very flexible, but it's the only complex where only doctor was able to find the correct pose on other products. Well, this system has an important point that this system has a metal cofactor. And Dr. use a classical force field that see the electrostatic, the van der Waals, and Dr. It's seeing correctly the metal inside the receptor, and showing that some other programs have difficulties to deal with this type of cofactors. We tested the Dr. program in a benchmark of highly flexible peptides, more than 53 protein peptide complex, and we compare with the other state-of-the-art products, and the results of Dr. are very comparable to other state-of-the-art products like AirDoc, Glide, and Suplex, and performs products like Gold, or even AirDoc. These are complex where only Dr. was able to predict the correct pose, and these two are peptide systems that only Dr. and Glide are able to predict the correct pose. We also developed our own empirical functions to predict the light energy between the receptor and ligand. we developed a physical-based score where we tested many machine learning, orthodox machine learning techniques like neural networks, SVM, random forest, but we use only six physical-based descriptors. And we developed a general sort function for whatever protein with a training set of 2,764 complexes, with a training set of bit more than 2,000 complexes. But we also developed a short function specific for case and another short function specific for PPIs or for leaders that interact with open solvent interface appropriate. This is operative results in the course set, the 2013. It's a test set developed to compare many of the historical development in the literature, and within this set with 195 complex, our linear function has a Pearson correlation that 5, 6, and our best non-linear square function with the Rutherford technique has a Pearson of 0.7. But our linear is among the best linear functions described in the literature. Are non-linear very good, but there are other functions developed with linear learning techniques that have better results. But it's important to say that in the Dr. Web server, the function that we made available for the user was the linear one, because the idea that we observed that the linear function was the best, the error that we see when we are dealing with other type of proteins, other type of ligands, outside this small set. This linear scoring function generalize better the non-linear scoring function. That's why if you go to the doctor, our scoring function predicted, the binding prediction will be the linear one. During the pandemic, we provided for the community, the academic community, scientific community, 6 molecular types from SARS-CoV-2, the SARS-CoV-2 virus. We curated very well this more than 60 replication structures were provided. They are available inside the Dr. Web server. We have more than 6 here. We have 6 molecular targets, and we also investigated the mutations of the principal genomic variants, and we constructed also the structures. All this is available inside the doctor. And it's in this year, we published another paper where we increased the set of molecular targets. We have today 8 COVID-19 related targets for SARS-CoV-2 and 2 human related targets, and to help to develop chemotherapy against COVID-19. And inside the doctor, we will also provide for the users the FDA library of drugs and with drugs. Now we have the new version of 2023 with 2,083 drugs. More important, All these drugs are curated. We calculate the multiple population states and authors of all these structures. In fact, we have a library for containing 2,285 volumes. It's very important, this library, to perform repurposing experiments against any molecular target. To show the importance to have many more than one structure, in the doctoral website, we'll provide two structures for the main PAs, and we perform repurposing experiment with the library of the FDA. And here we have the 6LU7 and 6W3 structures. And we also have for imagination, for example, if you perform the docking with the 6LU7, the imagination is ranked in the fifth best component as the fifth best component, but with the dock, perform the dock experiment using the CW663, the imagination will be ranked only in the 100th best as the 100th best component. In fact, if you only see this result, imagination will be selected for example, experimental to be experimentally validated. But if you see this result, imagination will be discovered. This result is to show that why it's so important to perform experiments with more than one structure reflecting the intrinsically flexibility of the molecular target. This is another interesting result. It's a Paxlovid, in fact, it's Imatrevir. The structure of Imatrevir complex with the main protein was released in 2021. And we thought that, okay, let's see if we have the Imatrevir, one of the compounds that's inside the Paxlovid, if the two structures of the main proteins provided by the doctor will be able to detect the correct conformation. Here is the doc structure experiment with Dr. who gave a rate square deviation of 1.09, but if we use the two different complexes for 7 the result is very good, but it's not good. Very high FFC, but using this 6W63 structure, you have a very good prediction of the both, showing that our choice for the structure of the record are very, very good and are for almost for these compounds. We will be able to try to predict the code inside this enzyme. These are the statistical use of Dr. Last year we had more than almost 27,000 jobs submitted from people of many countries in the world. We have more than 1,800 registered emails. Many groups in Brazil and abroad are using the USL to perform these explorers. In last year, we had 113 unique citations in the law, and from these citations, we have 74 citations that effectively use the portal. And from them, we see that 24 are from Brazilian groups and 50 are from foreign groups, showing that the doctor has a Brazilian impact in groups in South Asia, in groups in Brazil, and also. In the last few years, there have been a significant growth of AI models. The AI-derived models that are in clinical trials. For example, this graph, we have which models
identified in phase 1, phase 2, or phase 3. And here we see which type of AI, for example, in Yale, we have the AI was able to, was important to discover new targets. Here, AI is important for design new small molecules, to design new antibodies, to design vaccines, and to perform, to detect molecules. These graphs are very important because they show the impact of artificial intelligence in the field of drug discovery. In my research group, we are working in 3 main topics, using artificial intelligence and using computational intelligence. The first one, the development of deep learning-based storage functions for biometric predictions. The second, deep generative capture using multimodal genetic algorithms. And the third is the torturing of ultra-large global virus, but I will show only the first two topics. Developing a deep learning storage function is a challenge because there are 2 main problems: ligand and protein bias. If this is a correlation of that set of CNN, and you have 0.7 of correlation. But if you only see for a ligand and you put your deep learning storage function, you obtain 0.5 showing that the deep learning storage function is capturing the results the most weighted in the ligand bias representing training set. Another problem that many will see that confirmed that the deep learning storage function is not seeing the interaction between the ligand and the protein. In fact, they are memorizing the training set. Yes. And this is a very big problem because if your storage function is not looking for interactions, the intermolecular interactions, they exist poor generalizations when evaluated on new substances, not similarity to the training samples. And we developed in our group a convolutional neural network for biometric prediction. Yes, we started with the 4,000 protein complex, and now we are using more than 70,000 molecular complex, and our results in test sets, default test sets is comparable with the best deep learning strategies published in the literature. But the most important thing that we felt a data strategy that was able to avoid to increase the ligand and the protein bias. Here we have, if you put only the ligand now, you have only a correlation of 0.2. You don't have the amino acid close to the ligand, also your correlation decreases. And more important, we are now seeing the molecular interactions. This is very important because it shows that our storage functions is capable to generalize better generalize when seeing a complex that is not present in the training set. And also it's important because now we can investigate the importance of particular functional group of the ligand or particular residues of the protein for their importance in the biometric concept. Another very important results that we performed the confusion matrix. We divided the ligand in strong, moderate, and weak according to the clear energy of interaction between the region and the reserve. Very important to see that we have 74% of accuracy in detect stronger as strong. And another important thing is that when we observe the 44.3% of weak stronger that are predicted as weak is false negative prediction. When we investigate in detail why the original papers of this complex, we see that many of them, the structure of the legal activity was wrong, and or the concept of division was wrong, and our structure was able to correctly detect the structure that we are evaluating is not as strong as we thought. This is a good result because when we are making a report screening strategy, your main objective is to detect the stronger ligands. Our export was good to detect strong ligands, but when we observe the correlation inside this set of strong ligands, the correlations only get moderate. Our conclusion is when we are detecting the mass ligands, you can think that some of them are really strong, probably more, a lot of them are strong, but you cannot think that they are correctly ordered. And the best way is to choose a small set of these ligands and perform molecular dynamics to calculate a more accurate for the theory of. We also developed in our group the novel strategy to generate a model from scratch that fits many or multi-objectives. In fact, the design is physically many multi-objective approach where we want to optimize the ligand that has potency and selectivity against many targets. We want that this ligand has a low binding affinity for human models, for example, or off-targets, enzyme, for example. We want to optimize the pharmacokinetic parameters. We want that the ligand was not toxic. We want that the ligand was easily synthesized. And the idea is to treat this problem as a multi or many optimization problem, where the multi-objective optimization is when we are dealing with always that deal with less than 3 objectives, and the main objective of optimization strategies is when we are dealing with more than 3 objectives. And we developed a new strategy where we cook our encoder that with many objective genetic algorithm. The encoder is a version of the encoder. Tá, vou terminar aqui. The idea is to reduce the molecule is made in a lattice space. We reduce the directionality and by a encoder, and by using the encoder, you can reobtain the molecular three-dimensional structure of the molecule. And you can use this lattice with the reduced dimensionality of this lattice space as a chromosome or in a main objective evolutionary algorithm to obtain generate new models. And oh, and okay, with that, it is always in a problem with five objectives, where we try to obtain a ligand that's very similar with a ligand that's very important against a molecular target that's very important for bacteria inhibition. And we try also to that this new molecule has a similarity with another inhibitor of the same enzyme, but which is also very important against the human protein, the molecule human protein. And we also try to optimize the molecular complexity, the synthetic acceptability, and the new likeness of this molecule. And the results show that the best results are when we use a main objective approach. Here we obtain a more complete several of these objectives, and we dock this new molecule against the molecular target. You obtain that the more important the molecular target interactions are present. This is the first page of the new version of the doctoral project. It is open. The idea is that this website will be an open site platform design. It will incorporate all the developments using artificial intelligence and multiscale intelligence for reconstructing genetic chemistry. And the idea is to provide special service for projects from the CNS and groups. This is a group of research, the scientific group, people, foundation, biologists, pharmaceutics, engineers, and many people from biology are very good at programmers. And thank you very much for your attention.
People cheers. So we have time most to questions or comments. Are there some, please?
Nice. Advances sort of here. I'd like to know if you have some, it's possible to create a library of Plenary IGIs and to use instead the flexibility of the active site. If it's possible to have some clusters from the environments, for example, conformational clusters, and generate from the side chains they use, maybe apply shell agents to supply the shoe, the shoe.
We have, I didn't show the result, we have developed a standard strategy where we only take account the a set of information from the protein, of the backbone protein. But we can introduce the conformational of the side chain, because you have libraries of tunnels available in the literature. You can use this rotational library to take into account your algorithm to collect that. Or you can, if you are using molecular dynamics, you can investigate the behavior of your side chain during the molecular dynamics, select the most global, and put this in your algorithm.
Because you can create the library specific for your guidance. You can perform the variants for longer, examples. That is the start of chance. This creates the clusters of variants. And then proceed specifically to your target.
Yeah, the two types of practice. If you do a longer molecular diagram, you can cluster the returns and use in your algorithm. But if you don't do it, if you don't have the molecular diagrams, you can use a library of returns of side chains. And I think it's very interesting to see if we use one or the other, if the results are the same or you have a significant improvements using the returns from the molecular diagrams.
Okay. Let's start the program again.
That's very
Okay. It's time to go on. Session is here.
Tá bom. Eu uso uma variação e aí várias. Então não tem nenhuma.
Começa de
Eu tenho a grade e eu o algoritmo foi desenvolvido para ser robusto. Então, a primeira coisa que você falou, eu não quero nenhum bias na escolha. A população é gerada aleatoriamente dentro da grid, deixa eu ver o que é. Aí, senão, eu saio desse lado, eu saio daquele outro, eu já sei onde é o sítio, eu quero. Como a gente tem aquele lance de um trabalho e vai de novo, é interessante que ele seja jogando, porque ele vai explorando todo o espaço para mostrar que aqui tem uma interessante. Talvez ninguém
tempo em geral, né? Porque ele passei todo o.
Mas a gente. O que a gente fez? Ele foi desenvolvido para desenvolvimento flexível. Se você não usa uma abordagem de algoritmo você simplesmente não consegue zero taxa de sucesso. E, ao mesmo tempo, ele teve aquela manutenção da diversidade, ou seja, eu evito que haja convergência prematura. Então, eu pago por isso, tem razão, mas, quando eu chego em grandes altamente flexíveis, onde todos os algoritmos falham, não está lá. Ou seja, eu sou um pouco mais caro, não é tanto assim, mas ele tem um range de aplicação maior. Foi a escolha de como modelador que eu fiz, e eu não vou recomendar. Porque pode vir me dar para você, se a gente comparar lá, a gente vai constatar. E quando é pequeno, a gente acerta. Quando é alto, a gente começa a errar e a gente puxa. Então, verdade, hoje com a gente está fazendo, com a gente aperta o botão e não corta a coisa. Acho que o tempo de levantar aqui já temos dois, já tem um novo, por exemplo. Pode ter como dar. Uma CPU vai levar 5 segundos. Entendeu? Agora, claro, você coloca várias o custo não é tão alto, vale a pena gastar. Antigamente, eu falei, o avanço computacional vai fazer com que a minha metodologia se torne competitiva. Mas ela já era.
Principalmente coisa.
Não, o problema não é segredo, gigantes complexos, com muitos graus de liberdade, com muitas ramificações.
Pode ter um milhão de
Aí o algoritmo é imbatível.
Não, é Região, você não sabe o tamanho dela. Quando falou, é uma coisa infinitesimal. São bastamentos pequenininhos, ele te leva. Mas você não sabe se você der um pouquinho mais, se ele está funcionando, entendeu? E é assim o motor. Aí é outro estudo, tá? Ainda mais
Eu já tinha combinado com ela.